This is an example of a precipitation type problem. All right, let's say we've got two solutions and we've got 10 mils or 10.0 mils, and we're looking at 6.00 times 10 to the negative 5 molar CaCl2. And in another container we've got 100 mils or 100.0 mils of 5.00 times 10 to the negative 7 molar Be3PO42. Now what we're going to do is we're going to take these solutions and we're going to mix them together in one other container. And what that's going to do is it's going to give us a 110.0 milliliter solution. That's going to be the sum of these. And what we're investigating is whether or not the concentrations of Ca2 plus and phosphate in this new solution will be sufficient to allow precipitation to occur. And we're going to figure this out by using the Q value once we figure out what the actual concentrations of calcium and phosphate in this solution are going to be. What you'll see is that the calcium will come from the CaCl2 and the phosphate will come from the Be3PO42. Not only do we have to figure out the concentration of calcium in the initial solution and the concentration of phosphate in the initial solution, we also need to figure out what happens to the concentrations after dilution occurs and we get a new volume. So that's going to be the two parts of the problem. I'm going to delete all this here. Alright, let's take a look at how we start. We'll start off with the calcium chloride. And what we first need to do is figure out how the calcium chloride breaks apart. Now calcium chloride, if I draw a picture of it, looks like this. It's Ca and two Cl's, and we know that Cl has a negative charge. We know that Cl has a negative charge. That means the total charge on the negative side is negative 2, which means the total positive charge will be positive 2 on this side, which gives us a 2 plus charge on the calcium. So we know that calcium chloride will break apart into, this is calcium chloride aqueous, it's going to break apart into Ca2 plus 2 Cl minus ions. Just count them up. We've got 1 calcium 2 plus and 2 chlorides over here. And that's what we're going to get. Now remember, what we're interested in is the calcium 2 plus. We actually have no interest in the chloride whatsoever. The calcium 2 plus we choose because it's part of the equilibrium that we're actually talking about, and that's the calcium phosphate equilibrium. So I'm going to go ahead and find the concentration of the calcium 2 plus in this solution. So what I'm going to do first is make sure that my number of moles are correct. Now if I've got calcium chloride, it's a one-to-one reaction. So for every mole of calcium chloride I have in the solution, I'm going to get 1 mole of Ca2 plus. Right, so I'm going to do a calculation that reflects that. Now I'm going to convert the concentration of CaCl2 into the concentration of Ca2+. Alright, so that's our concentration of CaCl2. And as we've already established, we'll get 1 mole of calcium 2 plus for every 1 mole of CaCl2. And that's from the reaction here. It's a 1-to-1 reaction. And that gives us 6.00 times 10 to the negative 5 molar Ca2 plus. Now the way this works out, if you look at it, I'm just going to concentrate on the units here. You've got moles of CaCl2 per litre. That's what the M is over here. Now here we've got 1 mole of Ca2 plus over 1 mole of CaCl2. So what you see here is that the moles of CaCl2 will cancel, and we're left with moles of Ca2 plus per litre, which is this right here. So the dimensional analysis works out fine for that. I'm going to go ahead and delete that. Alright, so now we're going to have to take this 6.00 times 10 to the negative 5 molar. That's the initial Ca2 plus solution, and now we've got to figure out what happens to it when we dilute it. Now if you remember what I said before, I said that we're going to take the 10.0 ml solution of calcium chloride and add it to the 100.0 ml solution of the beryllium phosphate. That means we are now going to go from a 10.0 ml solution to 110.0 ml. So what I've got to do is do a dilution type problem to figure that out. The formula for dilution, I'll just do this just pictorially for you so you know what's going on. So you've got a 10 ml solution, and it's going into be a 110 mils now, 110.0 mils. So we've got a certain amount of calcium 2 plus in here, and we're still going to have calcium 2 plus in here. It's just that now it's going to be a whole lot more dilute than it was. Now the formula we use to calculate dilution or concentrations after dilution is C1V1 equals C2V2. So what we've got here is the concentration in the 10 ml, which is 6.00 times 10 to the negative 5 molar, times, and we've got 10.0 mils over here. So this is the concentration in the 10 ml solution, and what we're looking for is C2, that's the new concentration, in the new volume, which is 110.0 mils. Now you'll notice I don't have to do any conversions of milliliters to liters here. You might think we had to because we've got moles per liter over here, but we don't have to do that because we've got milliliters on both sides, and they're actually going to cancel. So once we figure out, see, this will cancel here with this, and what we're going to end up with is a value of C2, but will be in molar, and it will be 5.45 times 10 to the negative 6 molar. As we'd expect, in the 10 ml solution, the concentration was 6.00 times 10 to the negative 5 molar, and now it's almost 10 times less. Now it's in 110.0 mils, so it's 5.45 times 10 to the negative 6 molar. So that is the concentration of Ca2 plus in our final solution. Well, that takes care of the calcium 2 plus. We still need to take care of the phosphate, and we'll do that by investigating the beryllium phosphate. And we'll do that in the same way as we handled the calcium chloride. I'm going to go ahead and erase all this. And we're now going to look at the beryllium phosphate. Okay, so here's what we know about the beryllium phosphate. Be3PO42. And when it breaks apart, well, let's have a look. We've got Be, Be, and Be, and we've got two PO4s. Now if we know that the charge on PO4 is 3 negative and 3 negative, that means we've got a total here of negative 6. That means that the positive side must be positive 6, and in order to make that positive 6, each of these is going to have to be a 2 plus charge. So now we've got our broken apart compound, so it's 3 Be2 plus 2 phosphates. Now we're not interested in the beryllium, all we're interested in is the phosphate. There it is there. Okay, so we're going to have to figure out first of all the concentration of phosphate in the original solution. So we're going to have to do the stoichiometry thing that we did earlier. So we'll start off with 5.00 times 10 to the negative 7. Molar Be3PO42 times. Now if you look at the stoichiometry, we get 2 moles of phosphate for every 1 mole of beryllium phosphate. So we're actually going to have 2 moles of phosphate here for every 1 mole of Be3PO42. What that's going to give us is 1.00 times 10 to the negative 6 molar PO4 3 negative. Alright, so you can see what we've got here is, because we've got this concentration of beryllium phosphate, and we know that we get 2 phosphates for every 1 beryllium phosphate that breaks apart. Now we're going to actually have 2 times the number of moles of phosphate as the number of moles of beryllium phosphate that we started with. So that gives us that concentration. Now remember, this is the concentration in the 100.0 mil solution. Now we have to see what happens when it gets diluted. So we use our C1V1 equals C2V2. The C1 is 1.00 times 10 to the negative 6 molar times the volume it's actually in, which is 100.0 mils. Now we're going to see what happens when we change that volume to 110.0 mils. And you see again the mils will cancel. We'll be left with 9.09 times 10 to the negative 7 molar. And as we'd expect, that's a concentration slightly less than what we started with, because we've gone from 100.0 mils to 110.0 mils. So a little bit less on the concentration over here. And this is what we've got for phosphate. Alright. I'm going to go ahead and delete all this. And we'll finish up the problem. Alright, so let's look at the data that we've got so far. We've got that the concentration of Ca2 plus in the final solution is 5.45 times 10 to the negative 6 molar. And we've got our concentration of phosphate final as being 9.09 times 10 to the negative 7 molar. Now what we need to do is calculate our Q value. We're going to assume obviously this is not at equilibrium, so Q is going to equal Ca2 plus cubed PO4 3 minus squared. And where we're getting that from is the original equation. Remember, we're trying to see if this solid is going to precipitate. In order to do that, we need to look at the concentrations of the calcium and the phosphate. So the cubed comes from the coefficient and the squared comes from the coefficient. So I take these values and I plug them in. I got 5.45 times 10 to the negative 6. That one's cubed. And we've got 9.09 times 10 to the negative 7. And that one's squared. And what we're going to come up with as a final answer there is 1.33 times 10 to the negative 28. And this is the value of Q. So our next step then is to look at the value of Q and compare it to KSP. As you can see, the value of Q is less than KSP. Therefore, precipitation will not occur. Please go back and take a look at the previous mini lecture, and that will give you an explanation as to what the relationship between Q and KSP and when precipitation will occur and when it won't occur.